So in this video we're going to look at going the other way. So we have a polar equation and we're going to go back to a rectangular equation. So how do I know this is polar? Because the variables are r and theta. So I need to go back to rectangular. So I want to get cosine and x and y. So remember, x equals r cosine theta. So there's r. This is secant, but remember, secant is 1 over cosine. And now if I multiply both sides of this equation by cosine, I'll have r cosine theta. And then if I divide by 2, I'll have 1 over 2. So it's just this equation I multiplied by cosine, and I got 2r cosine theta equals 1. Then I divide by 2 and I get r cosine theta equals 1/2. And that's x. X equals 1/2. So what is this? This is the vertical line. X equals 1/2. So we have switched it from an equation that originally contained theta and r into an equation that only contains x and y. Now this one doesn't contain y because it only had r cosine theta, but that's how we would do it. We would try to create those r cosine thetas, r sine theta look into the equation. All right, now these equations are kind of unique, but r equals 3. We've already talked about what that would, if you graphed it into Desmos, it would give you a circle with radius 3, and we talked about that's what r is. R is like the radius, and the radius is constant. It's always 3. So if I rotate it around 0 to 2 pi, I would cut out a circle with radius 3. But I want you to see that I could also make this into the equation of a circle centered at the origin with radius 3 by if I squared both sides of this. So squaring both sides of a, I would get r squared equals 3 squared, which is 9. And then what is r squared? Remember in the previous lesson we saw that r squared is x squared plus y squared. So x squared plus y squared is equal to 9. That is a circle with radius 3. That's the rectangular version of that equation. And then b, if I just have theta equals, not just r, but theta equals, what do I do here? Well, I can write that as tangent of theta equals the tangent of 2 pi over 3. So I'm taking the tangent of both sides. And then again, if you look at your unit circle, here's my unit circle. The tangent of, if you open this up, we're looking at 2 pi over 3. There's 2 pi over 3. The tangent of that is negative square root of 3 over 3. So the negative square root of 3 over 3, I'm going to move that over here, is what that right-hand side becomes. This is negative square root of 3 over 3, or negative 1 over the square root of 3 if you want to do that. That's the tangent of 2 pi over 3. What's the tangent of theta? It's also defined to be y over x. And then I can multiply both sides by x, and I get y equals negative square root of 3 over 3 times x. And this is a line. Y equals negative square root of 3 over 3 times x. That's just a line that comes out of the origin. And its radius is not defined. It doesn't give a value for r. So if I go out on this line, negative square root of 3 over 3, I'd get that. But because r is not defined, I don't have to just stick to the unit circle. I can go up and down forever, and this just becomes a line. So this is defining an angle. So if you think about it, if we just defined an angle, let me just draw this for you real quick. So there's my x-axis, and 2 pi over 3, that would be, again, over here. That's just defining an angle. But because we're not defining a radius, I could go on forever at that angle in this direction. And because it doesn't give it a value for r, it could be negative as well, and we would be able to go that way because of the negative value, and we just get a line. So just an angle with no implied value for r, that gives me a straight line. Just an r with no implied value for the angle, that's a radius, that's a distance from the origin, and if we just go around at any angle that distance, we would cut out a circle. So this is just a circle, and this is just a straight line with that angle of inclination off the positive x-axis. All right, the last part of this section, when we're graphing these polar equations, there are different types of very common polar equations that have these looks, sines and cosines, with constants being multiplied by the sines and cosines and then added or subtracted, and r being equal to these things. So this is just showing you what shapes we get, and then the orientation depends on if it's sine or cosine. If we're on the y-axis is our line of symmetry, or down here the x-axis being the line of symmetry. I strongly encourage you to use Desmos when you're doing these, so you can see Desmos's version of graphing these. So here I am. I got r equals a sine 2 theta. So if I type in r equals, and let's do 5 sine 2, and then you just type the word theta, T-H-E-T, and then as soon as I hit A, it switches to theta, and we see that rose. They call these roses. So that's 2 theta, and then if I did something like 5 theta, there's a 5-leaf rose, 8-leaf rose, and I could switch this to cosine. And if you notice on all of these, they all go up and down to that whatever number's out in front. So 5, notice that the farthest this gets out from the origin is 5. If I made this, 6.5, then they'd all go out to 6.5. I made it 10, they'd see them all go up to 10. Okay, so that number is telling how far out these things are going to go. And then depending on this number that we see in here, we could get, it's not exactly how many petals it is, but it does alter the petals. Okay, so it does give us the right number for some, but for others it's double that number. And then the very last thing I want to talk about in this section is symmetry with the graphs of the polar equations. So symmetry about the polar axis deals with if you can replace theta with negative theta and the equation doesn't change. So if I were to graph, this is 1 plus 2 cosine theta. So if I were to graph that 1 plus 2 cosine, again just spell out theta, if I were to graph that and then change this, change this from theta to negative theta. Well, remember, the cosine of negative theta is the same as the cosine of theta, so nothing's going to change. The look of the graph doesn't change at all. So that's symmetry with respect to the polar axis, where we're rotating this thing from. So just to show you, if I were to do 1 plus 2 sine theta, all right, that does not have symmetry with respect to the pole. That graph and that graph are not the same. All right, the polar axis being the positive x-axis, it changes the graph completely. Okay, this graph is the same. If I have both of these guys change, then I am the same. So negative theta and negative r. So that means this thing has y-axis symmetry, if that's the case. So if you can change both, we have y-axis symmetry. If you can change just theta, it has, and then let me go back to cosine, it has symmetry about the pole, or the positive x-axis. Notice this graph doesn't have symmetry about the y-axis. But then there are some graphs that have symmetry about both axes. All right, here's the graph of the polar equation. R equals 3 times sine 2 theta. And you see if I negate the angle, nothing happens. So it has symmetry over the x-axis. If I negate r and theta, nothing happens. So it has y-axis symmetry. So some can have both x and y-axis symmetry if we can negate r and theta and get the same graph back.